All right, in vector calculus, basically the first thing we have to talk about is that there are two possible kinds of functions on which vector calculus can operate. There are vector functions where the parameter, we'll call it v, is actually a vector, and both its magnitude and direction can vary depending on where you are in space. And then it's also possible to have vector operations done on scalar functions. So here are some examples of vector fields. This would be, for example, a curve. And if you wanted to look, say, at the tangent to this curve, that's actually defined by a vector. So a tangent line would have both a magnitude and a direction in space based on the magnitude and the curvature of the curve. You can also have, if you have a surface, you can have a vector that's defined by the normal to the surface. If you have rotation, you can have a vector that's defined by the rotation in the system. The most obvious one to visualize is a velocity field. So if you have some physical thing and it's rotating, if you look at the velocity, that's a rotational movement. So those are the kinds of, just some examples, some visual examples of vector fields. Also important to note that they can depend on time. They can also depend on other parameters. So if this curve, for example, is moving or oscillating, then the field of the tangent vector to the curve can be time dependent. Similar, we can have a scalar function. Its magnitude is basically dependent on its location, the location of a point in space. So an example might be air pressure, temperature, density of a fluid, things like that. So here there's no direction or movement involved, but the property can vary over space, and it can also sometimes vary over time. So the first definition to make is the definition of Euclidean distance. So this is a scalar function. Basically, this is the physical distance between 2 points. It's based on the Pythagorean theorem. So basically, if we want to find f of p, if we have some either 0 point or reference point defined by x naught, y naught, and z naught, then we can find the distance between that point and a point at x, y, z by applying this formula for Euclidean distance in space. And it's possible that you can do this in a different coordinate system. So even if you did this in spherical coordinates, you basically would end up with the same difference. So the Euclidean distance is basically a scalar function depending on the location of the points only, um, and nothing else. Convergence, basically the definition of convergence. If we have some infinite sequence of vectors, it denoted a sub n, such that n is 1, 2, and so on, then the vectors are said to converge. If there is a vector such that as n goes to infinity, the limit of a sub n minus a is equal to 0. That's referred to as the limit vector of the sequence, and it can be written as given in expression 5 here. So these are just a couple of vector calculus theorems. If these vectors are given in Cartesian coordinates, then the sequence of vectors converges to A, if and only if the three components converge to the corresponding components of A. So in other words, if this is in three-dimensional space, then the x component of your vector sum would have to correspond to the x component of A, the y component would have to converge to the y component of A, and so on. Oftentimes when we talk about convergence, we think about things going to 0. That is not always the case. Things can converge to a constant, or they can converge even to something that is a steady state. All right, so here we would write that the limit of v of t is L, and there is some neighborhood of t naught that's an interval on the t-axis containing t naught as an interior point. So in other words, this term t naught is an interior point, not necessarily an endpoint, that if you have a vector sum, your vector will converge to this vector L. All right, so a vector function v of t, so this is time dependence. A vector function v of t is said to be continuous at t equals t naught if it's defined in a neighborhood of t naught. So if we then introduce a Cartesian coordinate system, this vector v of t is continuous at t naught only if its three components are continuous at t naught. So in other words, you can't have one of the coordinate coefficients go unstable. They all have to be stable and they all have to be continuous. So if one goes to infinity, the entire vector function is going to go to infinity. All right, the derivative of a vector function. A vector function is said to be differentiable if the following limit exists. This is in time. So the vector function v of t is basically, this is just the derivative definition. It's just in this case, the function is a vector and not a scalar. And so basically the way you take a vector derivative is you take the derivative of each of its components independently. So for example, if a vector is equal to t squared, and 0, so this would be t I hat plus t squared j hat plus 0 k hat, then its derivative would be the derivative of each of the individual component coefficients. So you would have 1, you would have 2t here, you would have 0 here. So basically, let's go back and look at equation 10. That's what they're talking about. Equation 9 is here. This is basically just saying that equation 10 and equation 9 um, make sense and follow from each other. Also, all the rules then of differentiation, like multiplication by a constant, um, the linearity of the derivative, meaning that the derivative of u plus v is the derivative of u plus the derivative of v, and then all of the following, where basically once again this g should be a dot, so the derivative of u dot v prime is u dot, so this is the product rule from calculus applied to vectors. And the same, of course, for the cross product. It's a little bit different. So u cross v prime is u prime plus v plus u plus v prime. So get a little cross product term here. Here's the derivative of the triple product and its formula. So these are some that are not used every day, so it might be useful to keep up with this particular slide, or I'm sure that if you're looking at the textbook, there's probably a summary section that would list these formulas. All right, so now let's talk about partial derivatives. So suppose we have the components of a vector, v1, v2, and v3 is shown here. And let's say they're differential functions of n variables, differentiable functions, t1 to tn. Then basically the partial derivative of v with respect to tm is notated as follows. So we take the partial of v is the partial of v1, the partial of v2, the partial of v3. And the same holds for the second derivatives and so on. So this is just saying that in addition to the derivative applying independently to each component, a partial derivative would apply independently to each component as well. All right, we are going to skip over curves and arc length because in this class that's not really something that we're going to talk about or utilize. It's not that common to use this in electrical engineering. Sometimes in fields you will see this used, but it's a pretty narrow area. So we're going to skip up and talk about somewhere this. Here we go. We want to talk about the gradient, which is a directional derivative. So the gradient is applied to a scalar field, and what you're trying to get an idea of from the gradient is you're trying to get an idea of how the scalar quantity varies with respect to direction. So the gradient is the partial, and these are commas, not primes here. So you take a scalar f, and basically the gradient is noted by gradient f, or the inverted delta, which is sometimes referred to as nabla of f. So we have this gradient f. It's the partial derivative of f with respect to x for the x component, the partial of f with respect to y for the y component, and the partial of f with respect to z for the z component. And so what this is giving you an idea of is it's giving you an idea as a vector of the spatial variation. And so once again, the differential operator sometimes just denotes the following operation. So partial with respect to x I hat. So if we have gradient of f, then you would insert the f here with the operator, with the differential operator. So it is a directional. We can also do a directional derivative. So we can look at the partial of f with respect to x in some direction. Once again, we're not going to use a whole lot of that because we're not doing spatial stuff. So gradients are used in field theory because the electric field is basically the gradient of the electric potential. They're also sometimes used in the method of gradient descent, which is looking for a method of maximum increase of a function, particularly if you have a three-dimensional surface. And this, once again, can apply to n dimensions. Method of gradient descent is used to find local max and min, and sometimes it's used to find local max and min, particularly min, in large data or feature sets. So it's not any different to use something like the method of gradient descent on data analytics than it is to use the gradient in physical fields that we would think more associated with physics or mechanical engineering. So this is just says that if we let f of p be a scalar function and it has continuous first derivatives in some domain, then the gradient exists and is a vector. Its length and direction are independent of a particular choice of Cartesian coordinates. So if the gradient of f is not equal to 0 at some point p, it has the direction of maximum increase of f at p. So we can also think about the gradient as a surface normal. If we let a be some scalar function and we let f of x, y, and z represent a surface, then the gradient of f at some point p is a normal vector to that surface. This is useful in fields when you think about equal potential surfaces. When you take the gradient of the potential, then basically that points in the direction of the electric field. So for example, if we have a point charge, the equal potential surfaces around that are spherically distributed. So if we take the gradient of those potentials, then it is a radially directed three-dimensional field direction. So the gradient can be useful in space to give us directions of things. Particularly, the best example I can think of in electrical engineering is to find the gradient of electric potential so that we can determine the electric field. All right, we're going to stop the video here and we will discuss divergence and curl in the final video for the